Hello, hello, hello. Okay, okay. So I thought this isn't Fermat's little theorem. This is the application of Euler's theorem. This problem that I'm about to do is directly from the class. I'm going to better explain it, and then I have another problem that I'll go through a little quicker and just demonstrate more tricks and usefulness that you can do with modular arithmetic and why it is so fascinating and cool. Oh, it's making the infinite finite, and I love that to my core. So we want to find what x is um, under this equation, right? We don't know, and then it's mod 12 because we're in Z12. Pretty sure that's standard. But to get x by itself, we need to get rid of this 5 up here, right? So we need dun 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 5 inverse. And then we'll multiply that by 5. Those will become 1, and we'll find what x is. And of course, we'll have to multiply the 6 by 5 inverse as well. So first we need to check, does 5 inverse exist? Because it may not. And the way we check that is if it's a unit and we find if the GCD of 5 and 12 equals 1. Does it? I don't know. Yes, it does. These two are relatively prime. GCD of 5 and 12 is 1. So 5 inverse exists. Now we need to find it. Now, this is a little helpful. It's like an extraction from Euler's theorem. I'm going to write that out. So Euler says, oh, I'm using like pink and blue. I kind of like that. He says that u, a unit, to the power of his totient function. I don't know why Webster didn't say that that's the name of this function. He called it the phi function. You use phi, but it's called the totient function, is equivalent to 1 mod whatever that n you're looking at is. Okay, so you take the integer in that you're looking at, you find the totient function of it. When you raise u to that power, you'll get 1. This is quite cool. What we need for our problem is what is phi of 12? Well, I'm gonna write out. There isn't like at least as far as I'm aware, a quick way to discern this. You just kind of have to count the primes and such. So we have in 12 we have 1, 2 does not work. 3 does not work. 4, okay, the next one, that 5 works. 6 doesn't work. 7 is relatively prime. And then that should just end it because like 9 has a common factor of 3. So there are 4 of these. So I don't want an equal sign. So phi of 12 equals 4. So for this instance, we're going to take our u, which is 5. We're going to raise it to the fourth power. We know that this is equivalent to 1 mod 12. We can double check this. If you, I guess I could do that for you real quick. 5 to the fourth power is 125 times 5, which is 625. And then if we divide that, or let's just see what that times 12 is. Oh goodness, why did I say I would do this? That's going to be 52 times 12 plus 1 because that will equal 600. The 2 will get you 24, and then there's a plus 1. So we have a remainder of 1. The modular arithmetic works. Um, just to double check that Euler wasn't wrong, although there's no way that we would be this far into this class if that was true. But we want to know 5 inverse. How do I find the inverse of phi? Well, there's this like, I don't know if it's a corollary or like lemma or whatever, but if we go back to looking at what Euler said, we have u times by power rules phi of n minus 1. By power rule, that's equal to u to the phi of n, right? These are equivalent to this. That's really cool and actually really helpful because we just said that u to the phi of n is equivalent to 1. And what we know about inverses is that a unit u times something else, if you get 1, then that means that these two are inverses. And so the inverse of u is just u itself to the totient function of n minus 1. So we're going to take that and apply it right to 5. We say 5 times 5 to the, well, we're going to have Oh, wait, that's not 12. To the 4 minus 1. Well, I'm just going to put 3 actually, is equivalent to 1. Now, this should make sense because 5 times 5 to the third is 5 to the fourth. And that's what we set up above, right? That's really helpful. Now, that means that our inverse is just going to be 5 cubed, mod 12, I should say. Because 5 cubed is way bigger. 5 cubed is 125, right? That's technically the inverse of 5 under mod 12, but we want to know what that number is for real in the world of mod 12. 125 doesn't exist. It's going to be some remainder. Luckily, 125 is just equal to 120 plus 5, which is equal to 12 times 10 plus 5. So 5 inverse equals 5 mod 12. This isn't always the case, right? The inverse could be another number. It would have to be a unit, so it would have to be 1, 5, 7, or 11. Just happens to be 5 for 12. So now let's go back to our very top, the top equation. We have 5x is equivalent to 6 mod 12. And we know that if I multiply by 5 on the left side of both of these equations, uh, that these two fives will cancel and I'll get x is equivalent to 30 mod 12. And then since we're going to simplify, let's simplify this. What is 30 mod 12? Well, if you divide, there's going to be, let's see, 24 plus 6. So x is equivalent to 6 mod 12. And we did it. So I hope that kind of makes a little bit of sense. I was trying to roughly explain that. Um, let me know if I should like further explain just the mobility which I use to like answer what 125 mod 12 is, or even the 625. Like that's numerical fluency at its core. But just, like I would say college level numerical fluency where I'd say I'm quite good at doing these quick divisions and checks. There are tricks that you can do. I'm going to try and highlight some of those in this one. Also, if you end up taking number theory, Ella and Ada, I don't think Maggie can. I think we already talked about that. If you take it, Dr. Bergdahl or whoever teaches it will show you all of this in much better detail. Working in modular arithmetic is like the foundation of all number theory, which is what we're in algebra now. If we're looking at Euler and Fermat, who did huge work in number theory. So let's check. First, we want to find, I said, find 4 inverse, right? It's the same kind of structure. GCD of 4 and 9 does equal 1, so it exists. Yay! Next, by Euler, let's just jump ahead. So Euler, I'm gonna rewrite it again, but oh, what am I doing? Um, what am I doing? Oh, wow, I just like total brain like glitched there. But U to the phi of n is equivalent to 1 mod n. So we know that 4 to phi of 9 is equivalent to 1 mod 9. Cool. But we should figure out real quick what phi of 9 is. Also, I apologize for my ugly phi's. That's a better one. Ooh, that's sometimes they look like upside down twos because that's how I write my upside down twos. So I'm used to writing that, and it kind of like, yeah. Oh, that was a good one. So that's going to equal, let's see, 3, 6, and 9 all divide. I guess I should say 3, 6, and 0. Um, all are like factors, so those won't count. So we should get 6, right? Because that'll be 1, 2, 5, 4, 5, 7, 8. Yep, there's 6. Um, Now we know that 4 inverse is going to be equal to um 4 to the 6. Remember, it's phi of 9 minus 1, which is equal to 4 to the 5th minus 9. Now, here's like cool tricks that I want to show you with modular arithmetic. I don't know what 4 to the 5th is. I guess I could figure it out real quick. 64. No, I don't want to figure it out. That defeats the purpose. Although it's like, I think it's 1028 actually. Sorry, I couldn't help myself. Um, so let's instead, we can do this in baby steps, is how I like to think of it. Modular arithmetic doesn't care when you do it, it just wants you to do it all. We have to make sure we take 4 to the 5th. We can think of 4 to the 5th as 4 squared times 4 squared times 4 to the first, right? So what I want to look at is what is this first 4 squared mod 9? 16 mod 9. Um, that's going to be equivalent to, 7, right? Yay. Okay. Now 7 is now this 4 squared here. So we just got rid of this and now we have 7. We're going to square that. 7 squared equals 49 mod 9. And that's equivalent to 45 3 mod 9. And then now we're going to take that and multiply it by our final 4. Let's do that. Sorry, my brain just shut down again. What am I doing? 12 mod 9. And that equals 3 mod 9. Wait, that's not right. What? What did I do wrong? 4 is 7 squared, 49. Oh, it's not 3. Ah, that makes sense. I was like, that's wrong. Ah, is 4. Sorry, 45, and then 4 more. 4 mod 9 times that final 4, you get 16 again. And as we said, 16 is 7 mod 9. Yay. Okay. So 7 is 4 inverse. According to us, we can again, let's double check that. 4 times 7 is going to equal 28. If we divide that by 9, we're going to have 27 plus 1. This is 3 times 9. So, yep, they're inverses. You get 1 under mod 9. Okay, final step as we go back to that top thingy, 4x. 4x is equivalent to 3 mod 9. We're going to multiply by the 7 on both sides. I'm just going to, this is mod 9. I don't want to write it. Those are going to cancel out. You'll get equivalent to 21 mod 9. And then let's find out what that is. That should be, there's my 3. That's what I was mistaking. X is equivalent to 3 mod 9. Yay! We have done it. I particularly like this. I'll do my next problem where I use how like Fermat's little theorem is really cool with primes and giant powers. It's in cryptography. I'll get into that later. Anyway, thanks guys.